Hello everyone, in this video we will cover the section 3.8. In this section we will see two important applications that use second order linear differential equations with constant coefficients. One of the reasons that second order linear equations with constant coefficient are worth studying is that they serve as mathematical models of some important physical processes. Two important areas of application are in the fields of mechanical and electrical oscillations. First, we will interest in mechanical vibrations. We will model this by using the second order linear differential equation. So consider a body of mass m attached to a vertical spring hanging from a rigid support, which is pictured in here. Look at the second picture. This is the initial situation of the spring, and when we attach a mass to a vertical spring hanging from a rigid support here, so the spring will expand, you see, as a measure bigger L, you see. This is the initial situation whose length is little l, and after we attach the mass to the spring, so the length will be bigger than the previous situation since it expands, you see. And also when we apply an external force to the downward, you see, so the length will be bigger than the previous situation. So therefore we say the mass causes an elongation L of the spring in the downward direction, and this direction is accepted as positive direction. In the corresponding dynamic problem, we are interested in studying the motion of the mass when it is acted on by an external force or is initially displaced. Let u of t measured positive downward denote the displacement of the mass from its equilibrium position at time t. Okay, u of t represents the displacement of the mass. Okay, from here to this place, the displacement is stated by u of t, which is a function of the time. Okay, then u of t is related to the forces acting on the mass through Newton's laws of motion. First, let's remember the formula for the force, the net force. It is the multiplication of the mass and the acceleration a. And if you remember, the acceleration is the second derivative of the displacement if the object moves along a straight line, and you see it is moving along a straight line. Therefore we write the second derivative of the displacement function instead of the acceleration, and you see here. So we observe that both u and the force are functions of time, because a is a function of time. In determining the force, there are four separate forces that must be considered. To determine the net force, we consider four separate forces for this situation. What are the forces for this situation? So they are gravity force, the spring force, resistive force, and external force. The gravity force, you know, is the multiplication of the mass and the gravitational acceleration g. The weight of the mass always acts downward. Therefore, the gravity force is in the positive direction. Okay, the gravity force is in the positive direction. And if the spring force is equal to minus k times the length of the spring, which is written as L plus U, where k is the spring constant and u is the displacement of the mass from its equilibrium position. Instead of the weight of the mass, we write L plus U, which is the length of the spring, and minus K is actually corresponding to the acceleration of the spring, and U is the displacement of the mass from its equilibrium position. The spring force is assumed to be proportional to the total elongation of the spring and always acts to restore the spring to its natural position. And the damping or resistive force always acts in the direction opposite to the direction of motion of the mass, namely the third one, the spring force. The resistive force is in the opposite direction. Also the spring force, F spring. In any case, we assume that the resistive force is proportional to the speed, which is the derivative of the displacement of the mass. This is usually referred to as viscous damping. If the derivative is bigger than 0, then U is increasing, so the mass is moving downward. So resistive is directed upward and is given by minus gamma times the first derivative of U, where gamma is a positive constant of proportionality known as the damping constant. And the last one is an applied external force is directed downward or upward as f of t is positive or negative. This could be a force due to the motion of the mount to which the spring is attached, or it could be a force applied directly to the mass. Often the external force is periodic, namely anybody can apply a force to the mass, which is called the external force. So the net force is the addition of them. By considering the negative and positive directions, we write minus or positive, you see, for every separate force here. So the gravity is in the positive direction, therefore we write m times g. And spring is in the negative direction, so we write minus k times L plus U. And resistive force is minus gamma times the first derivative and the external force. Writing them to the left hand side except the external force, so we find m times the second derivative minus m times g plus k times L plus U plus gamma times U prime is equal to the external force. And we know the net force, it is the multiplication of the mass and the second derivative, therefore we obtain this thing. So this is the second order non-homogeneous differential equation with constant coefficient. When the mass is in equilibrium, two forces balance each other, namely the spring force will be equal to the gravity force. So we write m times g minus k times L is equal to 0. Therefore k is equal to m times g over L. Therefore the mechanical vibration will be, after writing this, so we have m times g for the first part here. Also we have negative version of this number, this term, therefore we can remove them, so we have just m times the second derivative of u times k times u and gamma times u prime is equal to the external force. If the external force is equal to 0, namely we don't apply any external force for the mass, then the motion is called free. If it is not equal to 0, then the motion is called forced. Okay, this is our formula for determining the motion of the mass attached to a vertical spring hanging from a rigid support. Okay, we can model this event by using the second order linear differential equation you see. For example, a mass of 100 grams stretches a spring 5 centimeters. If the mass is set in motion from its equilibrium position with a downward velocity of 10 centimeters over second, and if there is no damping, determine the position u of the mass at any time, and when does the mass first return to its equilibrium position. So you know the value of mass, which is 100, m is equal to 100, and it stretches a spring 5 centimeters, which is written as bigger L is equal to 5 centimeter, and there is no damping. This is another information. Therefore, we write gamma is equal to 0. And we don't have any external force according to the example, which means bigger f of t is also equal to 0, and we can find the constant k, which is the spin constant. Yes, the spin constant. So according to the formula written here, it is equal to m times g over L, m times g over L. M is equal to 100. G is the gravitational constant, and we should be careful when we write the value of this gravitational constant. We should look at the units of the quantities written here. M is 100 gram, L is centimeters. Therefore, normally it is equal to 9 over 8 meters over second, I guess. So we should write 980 over 5 centimeters. Okay, 5 centimeters. So from here we obtain 19,600. 19,600. Okay. So now we can write the differential equation, since we have all of the constants written in the formula here. We have m, we have gamma, and we have k. So from here we can write m is 100, L is equal to 5, and k is equal to 19,600. So if you write the formula here, m times the second derivative plus gamma times the first derivative plus k times u is equal to f of t. F of t is equal to 0. K is equal to 19,600. Gamma is 0, therefore you know the second term. M is equal to 100. Therefore, the differential equation becomes 100 times the second derivative plus 19,600 times u is equal to 0. When we solve these differential equations, we will find the displacement of the mass. Okay, so how can we find the differential equation? So this is linear homogeneous second order differential equation with constant coefficients. Therefore, let's find the characteristic equation of this differential equation, namely 1 100, the second derivative plus 19,600 u is equal to 0. So from here the characteristic equation will be r squared 100 r squared plus 19,600 is equal to 0. And from here we obtain r squared is equal to minus 196, which means we have actually complex roots, namely r will be square root of plus minus square root of minus 196. Okay, and from here we obtain plus minus 14i, plus minus 14i, which means here alpha is equal to 0, beta is equal to 14. If you remember the formula, the solution will be u of t is equal to c1 times e to the power alpha t times cosine beta t, namely cosine cosine 14t plus c2 times sine 14t, according to the formula, if you remember from the previous sections. And at the beginning the displacement will be 0, which means u of 0 is equal to 0. Okay, and we know the speed of the according to the example, we have the velocity of the mass, which is 10 centimeter over second. Therefore at the beginning the speed, which is the derivative of the motion, will be equal to 10. Therefore we have the initial conditions. So when we write 0 for t, so we obtain, namely we will find the constants c1 and c2 by using the initial conditions. 0 is equal to c1 times 1, cosine 0 is equal to 1, sine 0 is equal to 0. So from here we obtain c1 is equal to 0. And therefore we have u of t is equal to c2 sine 14t, and the first derivative is equal to c2 cosine 14t times 14. And when we write 0 for t, and the first derivative will be equal to 10 here, so we write cosine 14 c2, which means c2 is equal to 5/7. So the displacement of the mass with respect to time is equal to 5/7 times sine 14t. At any time we can find the displacement of the mass attached to a vertical spring hanging from a rigid support by using this function. You see, by using the second order differential equation easily we can determine the displacement of the mass just by finding the value of this function at any time. Okay, therefore we have this function. So to find the time t, when the second question is that when does the mass first return to its equilibrium position? After a while the mass will return to its equilibrium position. So to find this time when the mass returns to its equilibrium position, we solve this differential equation by equaling the number 0. So from here we obtain, to get 0, sine pi is equal to 0. Therefore 14 times t1 is equal to pi, which means t1 is equal to pi over 14 seconds, which is approximately equal to 0.224 seconds. After 0.224 seconds approximately, the mass will return to its equilibrium position, to beginning position. Okay, no, the equilibrium position, by using this formula. Okay, the second application is to model the impressed voltage in a simple electric circuit. A second example of the occurrence of second-order linear differential equations with constant coefficients is as a model of the flow of electric current in the simple series circuit shown in this figure. We have a simple electric circuit. There are some quantities here like resistance, capacitance, inductance, and impressed voltage. The current I, measured in amperes, is a function of time. The resistance, measured in ohms, the capacitance, measured in farads, and the inductance, measured in henries, are all positive and are assumed to be known constants. The impressed voltage, measured in volts, denoted by bigger E, is a given function of time. Another physical quantity that enters the discussion is the total charge, Q, measured in coulombs, on the capacitor at time t. The relation between charge and the current is stated here. The current is equal to the derivative of the charge, total charge, with respect to time. The flow of current in the circuit is governed by the Kirchhoff's second law. In a closed circuit, the impressed voltage is equal to the sum of the voltage drops in the rest of the circuit. So according to the elementary laws of electricity and according to this law, we will determine an equation that states the situation. According to the elementary laws of electricity, we know that the voltage drop across the resistor is the multiplication of the current and resistance constant. The voltage drop across the capacitor is Q over C, and the voltage drop across the inductor is L times the derivative of the current. Hence, by Kirchhoff's law, we will add them, and they will be equal to, the addition of them will be equal to the impressed voltage, which is E of t. And the units have been chosen so that 1 volt is equal to 1 ohm and 1 ampere is equal to 1 coulomb over 1 farad, and it is also equal to 1 Henry times 1 ampere over 1 second. Okay, when we add them, we obtain this equation, and we know the current is equal to the derivative of the total charge with respect to time, dq over dt. Therefore, instead of di over dt, we write the second derivative of the total charge, which is written as L times q, the second derivative of q, plus r times the first derivative of the total charge, plus 1 over c times q is equal to E of t for the charge Q. And the initial conditions are written here. Thus, we must know the charge on the capacitor and the current in the circuit at the same initial time t0. This is our differential equation that states the situation for the simple electric circuit here. Namely, our formula is L times the second derivative of the total charge plus R times Q prime, where L and R are the constant. Also, C is another constant, is equal to E of t. For example, a series circuit has a capacitor of 0.25 times 10 to the power minus 6 farads, which means the capacitor is stated by C. This is equal to C. Okay, we know one of the constants given in the example. A resistor of 5 times 10 to the power 3 ohms, which is R in the equation. You know R. And the inductor of 1 Henry, namely L, is also equal to 1. L is equal to 1. We know the constants now. And the initial charge on the capacitor is 0, which means Q of 0 is equal to 0. If a 12 volt battery is connected to the circuit and the circuit is closed at t is equal to 0, determine the charge on the capacitor at t is equal to 0.001 second and at t is equal to 0.01 second and at any time t. Okay, so we know the impressed voltage, which is 12 volts. Also, it is equal to 12 volts. So we know the differential equation, and we can find the charge by using this differential equation at any time. Okay, so let's write here L is equal to 1, so we write the second derivative of Q plus R times the first derivative. R is equal to 5 times 10 to the power 3. 5 times 10 to the power 3, the first derivative, plus 1 over C, 1 over 0.25, which is equal to 1 over 4 times 10 to the power minus 6, 10 to the power minus 6. Q is equal to 12, equal to 12. So from here we have the second derivative plus 5 times 10 to the power 3, the first derivative, plus 4 times 10 to the power 6. Q is equal to 12. So the right hand side of this differential equation is not equal to 0, therefore this is a non-homogeneous differential equation, and we have constants for the dependent variable in this equation. Therefore we can use the method of undetermined coefficients to solve this differential equation, the method of undetermined coefficients. Undetermined coefficients. According to the method of undetermined coefficients, The first step is to find the solution of the corresponding homogeneous equation. By removing the right hand side, namely we write 0 for the right hand side of this differential equation. So let's find the characteristic equation. It is equal to r squared plus 5 times 10 to the power 3 times r plus 4 times 10 to the power 6 is equal to 0. So from here we should find the middle term after finding the factors of this number. Let's write 4 times, so we have 10 to the power 3, so we can write 4 times 10 to the power 3, 1 times 10 to the power 3. So from here we obtain r plus 10 to the power 3 and r plus 4 times 10 to the power 3 is equal to 0. So the solution of the corresponding homogeneous equation will be r1 is equal to minus 1000, r2 is equal to minus 4 times 4000. Therefore we write e to the power minus 1000t plus c2 times e to the power minus 4000t. Okay, this is the solution of the corresponding homogeneous differential equation. And the second step is to find a particular solution for this non-homogeneous differential equation by using the table which is stated in the previous sections according to the method of undetermined coefficients. So we have 12 can be considered as a constant polynomial, namely p and t is equal to 12. P and t is equal to 12. Therefore we use the first possibility in the table, if you remember, since we have a polynomial for the right hand side of the differential equation, which means n is equal to 12 and the number 0 is not a root of the characteristic equation, therefore s will be equal to 0. So the solution, the particular solution will be namely p, or we have q here, qp of t, actually qc, we should say qc of t, qc is equal to t to the power s, which is equal to 0. Therefore t to the power 0 is equal to 1 times n is equal to 0. Sorry, n is the degree of the polynomial, therefore we should write 0. N is the degree of the polynomial, therefore we have just a 0. So the particular solution is just a constant. Easily we can find the constant. The first derivative is 0 and the second derivative is also equal to 0. Therefore writing them into the equation, the differential equation written here, the second derivative is 0, the first derivative is 0, q is a 0, q is a 0. So from here a0 times here 4 times 10 to the power 6 is equal to 12. So a0 is equal to 3 times 10 to the power minus 6. Okay, 10 to the power minus 6. So the solution q of t is equal to the solution of the corresponding homogeneous differential equation and the particular solution obtained by the method of undetermined coefficient. So from here we have C1 times exponential minus 1000 t plus C2 times exponential minus 4000 t plus the particular solution, which is 3 times 10 to the power minus 6. Okay, this is the solution of the differential equation, and we know the initial conditions, I guess. The initial conditions: q of 0 is equal to 0, q of 0 is equal to 0, and q of 0 is equal to 0, and the first derivative, the value of the first derivative at the beginning time is also equal to 0, since we don't have any current flow at the beginning. Therefore we can write the first derivative at 0 is equal to 0. After finding the constants using the initial conditions, so we obtain C1 and C2 are equal to the numbers written here, which means we have the differential equation for the charge in a simple electric circuit given in the example by using the formula, which is a mathematical model for this simple electric circuit by using the second order linear differential equation. Thank you very much.